Welcome back. In this video, we continue our study of Chapter 1 and we move to Section 1.4 about accumulation points and subsequences. Okay. We already defined the notion of a convergent sequence and the concept of a limit. What does it mean to say that x is a limit of a sequence xn? It means that every neighborhood of x contains xn for all n starting from a certain rank. So for all n large enough. Or if you like, U contains xn for all n except finitely many of them. Okay, so in particular, the set of indices n such that xn is in U, is in the neighborhood, is infinite. Okay, so if you take this as a definition, we get the notion of accumulation point or cluster point. So, given a sequence xn of a metric space, we say that x is an accumulation point or a cluster point of the sequence if every neighborhood of x contains xn for infinitely many indices n. And there's another way to express this infinited, if you like, is to saying that for every neighborhood u of x and for every integer n, we can find a bigger index m such that xm is in U. Okay, so same thing as saying that the set of indices for which xn is in U is infinite. Okay, because this is the condition of infiniteness, if you like. Okay, so no matter what, if this set is infinite, then no matter what is the index that you give me, I can find a bigger one which is in the set. So of course, this is a weaker condition than the notion of convergence to a limit. Okay, so it should be clear from the definitions that a limit of a sequence, if the sequence is convergent, its limit is an accumulation point, and actually it's the unique accumulation point. Okay, but the converse is not true, and here are two trivial examples. If you take the sequence, the alternating sequence 1 minus 1, 1 minus 1, then it's not convergent, but it has two accumulation points. Why? Because if you take any neighborhood of 1, 1 minus epsilon, 1 plus epsilon, it contains x2 sub n, if you like, for all indices n. And same thing for minus 1. So here we have to distinguish between infinitely many terms of the sequence and infinitely many indices, okay? Because the sequence can be for example, here in this case, it just takes two values, 1 and minus 1. But the set of integers, the set of indices for which xn equal 1 is infinite. And the set of indices for which xn equal minus 1 is also infinite. Okay, another example, take the sequence 1, 2, 1 plus 1 half, 2 minus 1 half, 1 plus 1 third, 2 minus 1 third, and so on. So you see the pattern here. So here again, it's not difficult to see that 1 and 2 are accumulation points of this sequence. Okay, because any neighborhood of 1, for example, 1 minus epsilon, 1 plus epsilon, will contain 1 plus 1 over k, if you like, for all k, such that k is bigger than 1 over epsilon. And same thing for 2. Okay, now it's possible that a sequence need not have an accumulation point. So the set of accumulation point could be empty, could contain just one element, could contain two elements, and also could contain infinitely many elements. Okay? So how to characterize the set of accumulation points of a sequence? So here's a useful result. If we are given a sequence xn of a metric space, the set of accumulation points can be written as an intersection of a decreasing sequence of closed sets. Okay, a very useful result that we may need later in compactness. So we can write A as the intersection of the closure of the set xn, xn plus 1, etc. Okay, how do I prove that? It's very easy. I go back to the definition, so by a sequence of equivalence. So call the set xn, xn plus 1, etc. Call it Fn. Okay, what does it mean to say that x is an accumulation point of the sequence? It means that every neighborhood of x, for every neighborhood u of x, and for every integer, we can find a bigger index m such that xm is in U. And of course, we can put here strictly bigger. Okay, because if instead of n, you can take n plus 1. Okay, So now if I interchange the order of the quantifiers for every n for every u, what does it mean that there exists an index m bigger or equal than n such that xm is in u? Xm is a point, if m is bigger than n, then xm is a point in Fn, because the sequence is decreasing here. Okay? So it means that xm is a common point between Fn and u. So this condition can be written as every neighborhood of u intersects Fn for every n. And by proposition 1.8, this precisely means that x belongs to Fn bar. But this is true for every n, so this is equivalent to saying that x belongs to the intersection of the closure of Fn. So very simple. Okay, now we move to another related concept, that of a subsequence of a sequence. Okay, so given a sequence xn, so the index range through the non-negative integers or the positive integers from 1. Let us say that, to simplify, we can start from 0, from 1, from anything, but let us start from 1. And if you have an increasing sequence of indices, of integers, n1, n2, etc., then when we restrict the index to this collection, n1, n2, we obtain what we call a subsequence. So another way of looking at subsequences is that we write the sequence first in a list, x1, x2, x3, etc. And as we go along this list, we are allowed to cancel or to delete certain elements. Okay? And what remains is actually the subsequence. So for example, if you take the sequence, just the natural sequence of integers, 1, 2, 3, etc., and you delete the terms with even index. So you delete x2, x4, etc. So what remains is x1, x3, x5, etc. And so what we get is a subsequence which is just x sub 2n plus 1. If you take the same sequence and delete the terms that do not correspond to a power of 2, so we start from 1, 1, 2, 3, etc. We delete 1. Okay, we don't need to delete it, but if we start from 1, okay, so 2 to the 1 is 2. So 2 is a power of 2, so we leave it. 3 is not a power of 2, so we delete it. 4 is 2 to the power 2, so we leave it. 5, 6, 7 are not powers of 2, so we delete them. 8 is 2 to the power 3, so we keep it, and so on. So we get the sequence 2, 4, 8, 16, 32, 64, etc. So this remaining sequence is a subsequence of the original sequence of integers. Okay? And now, what is the relation between accumulation points and subsequences? Okay, this is the result of this section. So the two conditions are equivalent. Saying that x is an accumulation point of the sequence is equivalent in a metric space to the fact that there is a subsequence xn that converges to that point x. In general, 2 implies 1 in any topological space, but 1 implies 2 in metric space. So we'll prove that 2 implies 1, 1 implies 2. So 2 implies 1 actually holds, and more generally, in any topological space. So if xnk is a subsequence of xn that converges to x, then it means that for every neighborhood u of x, starting from certain rank k0, x and k will be in the neighborhood. So pick a neighborhood u, and pick an index k0, starting from which all the elements of this sequence x and k are in. So it means that if m is in this infinite set nk0, this is a set of integers of indices. So nk0, nk0 plus 1, nk0 plus 2, etc. So the difference between any two terms is at least 1. It could be strictly bigger, okay, as we saw. So it means that for every m in this set, xm is in u. And this set is, of course, infinite. Okay, so 2 implies 1. And the argument is very general. Now, in a metric space, the converse is true. How do you know that? We write the condition that x is an accumulation point of xm. Okay? And now we take u to be the ball of center x and radius 1, and we take in this condition n equal 1, because we have a freedom in choosing n. So by the condition, there exists an integer that I call n1, bigger or equal than 1, such that x and 1 is in this ball, in the neighborhood. And in the next step, take q to be the ball of center x and radius 1/2, and take n to be the previous integer, n1 plus 1. Then there exists a bigger index, n2, such that x and 2 is in the ball of center x and the radius 1/2, and you guessed the procedure. Okay, so at the k step, we take the ball of center x and the radius 1 over k, and we take n to be the previous integer plus 1, and therefore there exists another index nk bigger than nk minus 1 plus 1, such that x and k is in the ball of center x and radius 1 over k. So by construction, the distance between x and k and x is less than 1 over k. So as k tends to infinity, x and k converges to x. So we have now a subsequence. We constructed a subsequence converging to x. Okay. Now, of course, if I put instead of bigger or equal, strictly bigger, because it's equivalent actually, I don't need to take plus 1 here. Okay. But you know that the two conditions are equivalent. I can put strictly bigger or bigger or equal, same thing, as you may check, because n is arbitrary. Okay, so this concludes the short section on accumulation points and subsequences. And so thank you for your attention, and see you next time.